All right. Hi, guys. My name is Ufuk. Thanks for the introduction. I also work with Till Data Artisans, and I'm a committer and PMC member at the Flink project. And today, thanks for taking the time first. Today, I'm going to talk about how to use the stream processor, in this case, Apache Flink, as a database, maybe replacing your database or supplementing it. And what I want to do today is two things. First, I want to give the motivating use case, how we came up with this. And then in the second half of the short talk, I will show you some code and how to use this. So, like the classical use case for stream processing is doing stuff in real time. And the application that's like a little bit more interesting than ETL is doing some counts or aggregates in real time. And this is also the motivating use case here. So in this case, you have a stream of events, for example, tweets with an ID, an event type, and the timestamp. And what you want to do with this is display this somewhere, for example, in your dashboard in Grafana, and really understand how this data evolves over time. And how you usually do this is you somehow collect the events, feed them into a message queue. This could be anything like Kafka, Dataflow, PubSub, or Kinesis. And as soon as you have the data in the message queue, you can use your stream processor to analyze this. And because this is Flink forward, we use Flink for this, of course. And in the end, if you want to actually present this data somewhere, you want to serve it in the dashboard, you need to put it somewhere else. This can, again, be anything, for example, Cassandra, MySQL, or Redis. And in code, this could look like this in Flink Scala API from top to bottom. You could have your custom type, an impression with an ID, and count the number of impressions. You add a source to your Flink program, reading this from Kafka. You do some very basic filtering, check the event type, and then actually create an impression out of this. And in the end, this is where it gets kind of interesting, is you split the stream up by the ID you're interested in, aggregate this in an hourly window, and then do the counting. After you have written this, Flink will distribute this for you. For example, in this case, over 2 nodes, you get a pipeline like this. And all the state for the hourly aggregates is kept in the window operators. And when you now actually want to serve this, what you have to do is you have to put it somewhere else. So in this simple example, it could be Redis. So you do all your analysis in Flink, periodically push the data to Redis, and do your queries to Redis. Because the windows in this example are quite long, for example, an hour, you have to do this periodically using, for example, a periodic trigger. And when you do this, it turns out that this can easily become a bottleneck in your processing pipeline, because you do this for every key, every 10 seconds or whatever. And in the end, this can easily bottleneck the pipeline. And this was the motivation. So what you do here is actually when you push this to Redis, you have the state already in Flink. In Flink's process memory, you push it to Redis and have it in Redis's memory. So there's not a lot you gain, actually. It's a simple key value lookup. And the idea was, if you have this in Redis, why don't we directly query this from Flink? And this is exactly what we are trying to do. And in the end, if we want to still put this to a database for long-term archival or something, this is still possible, but it's optional. So this relieves a lot of stress from your external system. And from the application's point of view, you have this a query service. This can talk to both Flink for the latest real-time results and also to your database or Redis for past results and older results. And this is now with Scalable State strictly optional. And what makes this actually easy in Flink is that Flink already has all the hard ingredients to make this work. So state is a first-class citizen already. This means that you can express your program if you want to, for example, do this hourly windows. This is just some lines of code to do this. It's a first-class citizen Flink. The state is fault tolerant. This means that if your Flink job crashes, it will be recovered again with exactly one semantics. State is partitioned. This is very important for the performance you get, and this makes the updates to the state only local to the thread that's actually dealing with the records. And it's also continuous, which means that your queries will always be available. So looking into this a little bit more detail, this could be again your simple Kafka Flink windowing job. Records flow through the topology record at a time. And if you update your state, for example, here in the window operator, you don't have any replication or synchronous writes. And Flink's checkpointing mechanism will make sure that your pipeline is actually not stalled when you do this, and you don't have to cross any process boundaries to make this work. So if you already have all of this, queryable state, or the implementation of queryable state actually becomes quite easy. So taking like a bird's eye view on Flink, you have these two components Till already talked about in the previous session, the job manager and the task managers. The task managers actually hold the state instances, and when you now deploy your job, the job will be deployed to the task managers. And what we need to do to access the state is actually just report the state to the job manager, add a query component that I will show in a minute. And this query component now has two main jobs: figure out where my state is and actually query it. So what happens, I think, now is if you can specify a query for a job and a state name. It will ask the job manager on the first query, where is this state actually located? The job manager will look this up, give it back to the query client, and now the query client can directly address the task managers and state. So this is actually just a very simple addition to Flink's state abstractions. Yeah, there's already a question?
So does it mean like all these jam files would be the class part of the query client as well? Like, because especially for the deserialization to work, right? It's not done by any of these guys, either task manager or job manager. So we should have those binaries in the class.
So the question is, what happens if you have like custom types that come from the user program? And it's a very good question. I'll get to it in a minute when I show the code, okay? Cool. So actually, I'll go to it after the next slide. And so we made some experiments exactly with this setup. We had some synthetic benchmark. We had some events ingested, did some windowing, and wrote the results to Redis. And it turned out that with the growing key space, the throughput we could get in the stream processor was very limited because of the communication with the key value store. And with queryable state, we were able to essentially get rid of this. So what you see here is we can get with 1 million keys, we got the same throughput without Redis, with Redis, with only 100 keys. So this was kind of the motivation for us to go to this direction. And yeah, let me just show you how this actually looks in practice. So what we have here, is this readable, or should I increase the font size in the back? Yeah? All right, cool. So what we have here is a very simple Flink job where we generate some data. The data we generate are impressions. So very simple data type, just a user ID and an item ID. We partition the stream by the item ID and then say, give me this as a queryable state stream under this name, and the state should have this type. Here we say counting state, and what this is, is also quite simple. It's a folding state instance. So you might have seen this before in the training or earlier today. It's a folding state instance where for each element that is received, you just update increment and count. The initial count is 0, and here you do the upgrade increment. So after you have this, we can just execute it, and the state is accessible under this name and the job ID and the key we're interested in. So this is what we're going to do now. So I just prepared a script for this. We say run the job. All right, so now we are generating some elements, roughly like 1 million per second. If we look into the Flink web UI, you will see that we have 4 local task managers running. And if you look at the job, we'll have a source that's generating the data and a creable state operator. In this case, this is just a simple flat map that forwards the elements to the state instance. And you see here that the source has generated until now like 32 million events, and we're consuming them with multiple task managers here. And now we actually want to query this. So there we don't start with the code, but with the result. This is just a simple query REPL. I forgot to add the job ID in this case. Just a second. So now we started the client. We are querying the item counts state instance in this example, and the keys we're interested in are 3-letter alphanumeric strings. So we could, for example, say LOL, this is a legal key. And what you see here is we're querying it, and we get a count back. In this case, I think it's not really readable. It's not right, but it's roughly 3,000. And if you do this again, you will see that this increases, in this case, to 3,500, and so on. And another interesting bit here is that the first query took a little bit longer, because here we actually do the lookup of the locations, and the following queries then know where it's located and queried it like way faster, in this case, a millisecond. The code for this is also pretty simple. So what you need in Flink is this queryable state client. You set it up to know where the Flink instances are running. And the client is fully asynchronous. So when you actually query your state instance, you provide the job ID, state name, and the key. Currently, this is rather low level, and you have to manually serialize the key. So this is also getting back at the question I was asked. So you have to know yourself in the client program how to serialize the types, both when you query and when you get the result back. So in this case, when we serialize it, we know that it's up here we know that it's a string. We set it to a string serializer, and it works. Because we want to access this synchronously, we wait on the future to complete and deserialize the value, and that's how we get it. Yeah, that was a rather short demo. To conclude this, so the takeaway from this talk should be that the stream processor is often not the bottleneck in most applications, so you can push it quite high, mostly in terms of volume. And usually, when you introduce other systems that you communicate with, this becomes easily the biggest bottleneck. And queryable state allows you to actually mitigate this bottleneck. And the performance is usually also very good because the ground truth comes from some kind of message queue, which can be made very fast because it's append only and it can be replicated in a streaming fashion. And the state updates in the stream processor are only local to the state because state is already partitioned. Yeah, that was all, and I'm happy to take some questions. Yeah, let's start here in the front.
The roadmap for this feature?
The roadmap for this feature is, we think it's quite important already and will become more important over time. I think immediate next steps will be to improve the API. So as you've seen, it's really low level. You get bytes back and have to serialize keys yourself. So I think there are some easy things we can do to improve this a lot. So I would expect this to be the next fix. Then currently, you cannot expose windows for queries. I'll expect that this will also change very soon because Windows right now use the same state mechanisms as regular user code. So these are two things where I think changes will happen quite soon. Yeah.
You mentioned the state is fault tolerant.
Yeah.
So say if, for instance, a task fails or it gets moved to re-execute in a different machines, how do you recover the state?
Yeah, very good question. So in this case, the query would go to a wrong task manager or a task manager that has already died, and we would ask the job manager again for the location, and then this would be redirected. So essentially, the client is aware of that this can happen and takes care of this for you.
So you're talking about rerouting. Okay, but my question is, how is the state recovered when that part of task is getting re-executed on a different box?
Okay, this is part of Flink's regular checkpointing mechanism and fault tolerance. So are you familiar with that?
Kind of.
If you want, we can talk about this offline because it does not directly relate to queryable state, but this is kind of taken care of by the checkpointing mechanism.
And then I have another question.
Sure.
So if this queryable state can serve as data store directly, but normally people still need to persist the data eventually to an external data store. So has anybody tried to use this queryable state as a buffer for writes to the permanent data store? Say you have a lot of updates. You don't need to send all the updates to the permanent data store.
There were actually 2 talks here at Flink Forward where people use this in production. I think one user is sitting here. It's Joe. You can also talk to him. And so the answer would be yes, people use this already.
You kind of answered this already, but just want to make sure. So is callable state operator kind of stackable with sync operator?
What do you mean stackable?
Just connecting a DAG.
Actually, like what I showed acts like a sync. So after you do this as queryable state,
Right.
You don't append any other operators after that.
But can you connect another sync operator to it?
You could do this, but then you would have to use another API. For this, you would have to call on do a regular operator on some state instance.
Right.
And there's another API call that I can show you where it says set queryable, and then you can just use it as a regular operator.
Okay. All right, cool.
So database usually have a high availability requirement. What if we need to redeploy the code or we need to upgrade in Flink infrastructure? What will happen?
No, definitely. This is like in very early days, and replacing a database is more a vision than like reality right now. So it's not highly available right now. So when the job manager goes down, you can't serve queries at the moment. So, but there are of course ways to work around this, and I can see that we might work on this in the future.
Is it possible to access the data in a RocksDB without going through Flink that was written to RocksDB by Flink?
In theory, yes, but it would be quite hacky. So, yeah. Flink usually cleans up after itself, so you would somehow have to tell Flink not to do this if you want to access this long term.
Do you recommend this method to share states between operator? Let's say one operator wants to access another operator's state.
It would definitely be possible to do this with queryable state. I've never done it, and I can see that it's challenging to give any strict consistency guarantees when you do this. So if you can live like without any consistency guarantees at the moment, you could do this. And if you want some, we would have to discuss it in more detail. Yeah.
So back to the other question that he had about a database being highly available. Theoretically, could you, because you have checkpointing, can't you restore from checkpoint and then reprocess a certain number of things you've lost and then recover that way?
Yeah, definitely. The data will be available again. And
right,
it will be
it's
consistent.
just the recovery cost, right?
Exactly. But during recovery, it will be not available.
Ah, yes.
Yeah.
Okay.
So you don't have high availability. The kind of data that you have.
Exactly. I mean, depends on how you define it strictly.
On the consistency part of it, right? So how is it internally implemented? Like, is it really talking to the checkpointed state, the global checkpointed state, or in-flight checkpointed state? Like,
Also very good question. Right now, it's simply in-flight, so to speak, uncommitted data. So it's not the last checkpointed state, but I could also see that we provide different modes of queryable state, where you say, okay, I only want to read committed data from the last checkpoint, or I will also be available to read uncommitted data, like isolation levels in databases, essentially.
So if it is not reading from the checkpoints at all,
Mm-hmm.
then why should, where is the job manager interaction really helpful? Like, if it's like just reading from the memory of the task manager nodes, let's say I have a list of elements, right?
Mm-hmm.
So we're talking about, hey, give me the record belonging, or list of records belonging to this user, right? So the job manager internally, the metadata it's sending back is just the task manager nodes metadata, or is it?
Exactly. The question is why we talk to the job manager at all, and this is usually only done like on the first lookup to get the location of the state instances on the task managers. And after you have this information, you directly communicate with the task managers.
Okay. We're restricted by time, so if you have any other questions, probably you can ask them offline. Thank you for the presentation.